The Tango Energy Modeller's principal role is to determine the power and energy consumption of applications which are running within the Tango framework. It does this by mapping the utilisation of resources to a given level of power consumption. This allows it to determine the application's power consumption based upon its utilisation levels. It also allows the forecasting of power consumption given a notion of how much utilisation is going to occur in the future. This whole process aids adaptation by providing an understanding of power consumption of applications. This power consumption of applications is then presented in the monitoring infrastructure and displayed through a Grafana interface. The first step in energy modelling requires a set of calibration data. The calibration process aims to achieve this. It works by setting fixed utilisation levels and measuring the actual power consumption. Establishing these fixed levels of utilisation is very important. This is due to the actual differences between the timings of the measured power consumption and the utilisation level. We need to ensure that these values are actually synchronized and that a given power consumption is actually representative of a specific utilization level. In the end, after we have done this process, we can actually get decent calibration data as shown in the graph. The calibration process also has to work for various other heterogeneous resources, for example GPUs. This requires the calibration process to have to be very flexible and to cope with various different data types coming in from the monitoring infrastructure. Neural networks offers the first possibility of actually ensuring a calibration is actually applied to the data set that's obtained. The user simply has to specify on disk what actual different metrics are going to be used to determine the power consumption. This then allows the possibility of it to train and then actually determine the best fit for the calibration data. If this isn't possible, there's a second option, which is the CPU and bimodal accelerator. It takes the assumption that the accelerator is principally made up of two individual states. For example, a GPU is either utilised or it is not. This has the advantage in that it allows a model to be formed with poor quality data. For example, we can see in this graph that there are two states shown, and we can see that a clustering mechanism would work to define these two regions. And once we determine the actual clock frequency of the GPU, we can therefore say which level of power consumption is likely to be achieved. This therefore works as a reasonable approximation to determine utilisation. So this clustering process is reasonable using the next graph. What we see is the estimated power compared to the measured power consumption. And we can actually show that it tracks reasonably closely. This therefore makes it a reasonable predictor of the current power consumption. This is particularly the case when you can consider that not all metrics can be gathered, which may actually be useful to actually determine a more precise power consumption. In this demo, we show two instances of the same application running, and we show the output in the Grafana user interface. That we have two jobs running, and this is showing the application power consumption and the host power consumption for this job. So we can see additionally that the energy modeler within the architecture is working. They both complete at roughly the same time, so no further record is given.